There's a dot at the center of every map, a point where all the lines converge, where coordinates meet at zero. But what if I told you the universe doesn't have one of these? No center point, no cosmic address marked, "You are here." The question seems simple enough. If the Big Bang happened, shouldn't there be a spot where it all began? Your brain wants there to be a center. Mine does too. We've spent our entire lives in a world where everything has a middle. Cities have downtown districts. Planets have cores. Even galaxies spiral around central points. So naturally, when we think about the universe itself, we imagine some cosmic ground zero. A place where the Big Bang went off like the mother of all fireworks, sending matter flying outward in all directions. But that mental picture, completely wrong. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. And here's what makes this so fascinating. The universe doesn't just lack a center because we haven't found it yet. It lacks a center because the very concept doesn't apply. Understanding why requires us to completely rewire how we think about space, expansion, and what the Big Bang actually was. Let me start with what the Big Bang wasn't. It wasn't an explosion in space. Picture a bomb going off in an empty room. There's a clear epicenter. Material rushes outward from that point. The farther you are from the detonation, the later the blast wave reaches you. That's an explosion in space. The room existed before the bomb went off. The space was already there. The Big Bang was nothing like that. It was an explosion of space itself. Not an event that happened somewhere, but an event that happened everywhere simultaneously. The room didn't exist before the bomb. The bomb created the room as it exploded. Your brain probably just glitched a bit reading that. That's normal. Think about it this way. If you could somehow rewind time back to the moment of the Big Bang, you wouldn't find yourself traveling to some distant cosmic location. You wouldn't journey billions of light years to reach the spot where it all started. Instead, you'd find that every single point in space was participating in the Big Bang. The room you're sitting in right now, that was part of the Big Bang. The space between distant galaxies, also part of the Big Bang. The Big Bang didn't happen at a location, it happened at a time. This is where things get weird. The Big Bang was a singular event in the history of every object in the universe. Take any particle, any bit of energy anywhere in the cosmos, and trace its path backward through time. Eventually, you'll reach the Big Bang, where that particle gets compressed together with every other particle in existence. But here's the crucial part. This is true for particles everywhere. An alien on a planet a billion light years away could do the same thing. They'd trace their particles back and find the Big Bang too. They wouldn't find a different Big Bang or a Big Bang in a different location. Same event, same time, different place. The cosmic microwave background radiation proves this. This ancient light is the afterglow of the Big Bang, radiation that's been traveling through space for nearly 14 billion years. And we see it coming from all directions equally, not from a single point in the sky, not stronger in one direction than another. Everywhere we look, we see the remnants of the Big Bang surrounding us like a shell. This radiation is the oldest light in the universe, and it's perfectly uniform in temperature to about 1 part in 100,000. If the Big Bang had happened at a specific location, we'd expect to see that radiation concentrated in one area of the sky. We'd see a hotspot pointing toward cosmic ground zero. We don't. The temperature is the same in every direction we look. So where does this leave us? If the Big Bang happened everywhere at once, then everywhere is the center, which is just another way of saying nowhere is the center. But surely we can find some kind of center, right? Some way to define a special point in the universe? Physicists have actually examined this question systematically, looking at every possible definition of what could constitute a center. None of them work. Let's start with rotation. If the universe was spinning, we could define a center of rotation. Picture a merry-go-round. There's a clear axis, a point that stays stationary, while everything else revolves around it. But observations show no rotation whatsoever to the universe as a whole. Galaxies aren't swirling around some cosmic axis. They're moving away from each other, but not rotating around anything. No rotation means no rotational center. What about curvature? A sphere has a center point, the spot equidistant from all points on its surface. But current observations indicate the universe is flat, not curved. At least it's flat on the cosmic scales we can measure. A flat geometry doesn't have a center in the way a sphere does. An infinite flat plane has no middle point. Every location is just as valid as every other. Then there's the expansion itself. Surely the universe must be expanding from somewhere. This is where our intuitions really lead us astray. The expansion has no center because space itself is expanding everywhere simultaneously. Here's the famous balloon analogy, and despite its limitations, it's worth understanding. Imagine the surface of a balloon with dots drawn on it, representing galaxies. As you inflate the balloon, every dot moves away from every other dot. But none of the dots are at the center of the expansion. From the perspective of any dot, all the other dots appear to be moving away. The expansion is happening everywhere on the surface at once. Now, you might object that a balloon obviously has a center. It's inside the balloon, in the three-dimensional space the balloon occupies. But remember, in this analogy, the surface of the balloon represents the entirety of space. There is no inside or outside. We're not three-dimensional creatures looking at a two-dimensional surface. We're two-dimensional creatures living on that surface, and for us, the surface is all that exists. The inside of the balloon doesn't correspond to anything in physical reality. This is where the analogy breaks down, because our universe is three-dimensional, not two-dimensional. But the principle remains. Just as the surface of a balloon has no center point on the surface itself, three-dimensional space has no center point within it. In 1929, Edwin Hubble made a discovery that revolutionized cosmology. He found that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship is now called Hubble's law, and it's one of the key pieces of evidence for the Big Bang. But here's what Hubble himself recognized. This observation doesn't mean we're at the center of the universe. At first glance, it seems like it should. Everything is moving away from us. Doesn't that make us special? Doesn't that put us at the cosmic center? No. And Hubble understood why. If the universe is expanding uniformly everywhere, then every observer, no matter where they're located, will see exactly the same thing. They'll see galaxies moving away from them in all directions, with velocity proportional to distance. An alien astronomer in a galaxy billions of light years away would look at their sky and see the same pattern, everything rushing away from them. They might be tempted to think they're at the center too. This is what uniform expansion means. There's no preferred location, no special vantage point. The expansion looks the same from everywhere because it's happening everywhere. The key concept that makes this possible is that galaxies aren't really flying through space away from each other. They're relatively stationary within space, and space itself is stretching between them. This is perhaps the hardest idea to grasp about cosmic expansion. We're used to thinking of space as a static stage where objects move around, a cosmic theater with a fixed backdrop. But general relativity taught us that space is dynamic. It can curve, warp, and stretch. When we say the universe is expanding, we don't mean objects are moving through space. We mean the space between objects is growing. Go back to that balloon. As you inflate it, the dots aren't sliding across the rubber surface. The rubber itself is stretching, carrying the dots along with it. The dots maintain their positions on the surface while the surface expands. In our universe, galaxies maintain their positions in space while space expands. This creates something beautiful and strange. Every point in space has an equal claim to being the center of expansion. Or, putting it another way, the center is everywhere, which means there is no center at all. But we do appear to be at the center of something, the observable universe. That's the spherical region around us from which light has had time to reach us since the Big Bang. It's roughly 93 billion light-years in diameter, and we're right in the middle of it. This might seem to contradict what I just said, but the observable universe isn't the same thing as the universe itself. It's simply the portion of the universe we can see, and by definition, we're at the center of what we can observe. An observer on the other side of the cosmos would have their own observable universe, a different sphere centered on them. These spheres would overlap, but neither observer would be at the center of the other's observable region. Think of it like standing in a dense fog. You can see clearly for 100 feet in every direction. You appear to be at the center of a circle of visibility, but someone standing a mile away also sees clearly for 100 feet around them. They're at the center of their own circle. Neither of you is at the center of the fog itself. The observable universe has a boundary only because light travels at a finite speed, and the universe has a finite age. Light from regions beyond about 46 billion light-years away hasn't had time to reach us yet. That's our horizon, but it's not an edge to the universe itself. It's just the edge of what we can currently see. And here's something that should make you pause. That horizon is shrinking in a sense. Because of dark energy, the universe's expansion is accelerating. Distant galaxies are being carried away from us faster and faster. Eventually, galaxies currently visible will redshift out of view entirely, their light stretched to wavelengths we can't detect. In the far future, if this acceleration continues, observers in our galaxy will see a much emptier sky. Most galaxies will have disappeared beyond the horizon. Those future astronomers might have no way to discover that the universe is expanding, no way to learn about the Big Bang. The evidence will have literally moved beyond their reach. We're living in a special time when the universe's history is still written in the sky around us. This brings us to a profound question. Is the universe infinite? If it goes on forever in all directions, then obviously it has no center. You can't point to the middle of infinity. But even if the universe is finite, it still might not have a center, depending on its shape. Cosmologists recognize three possible geometries for the universe based on its density and the equations of general relativity. If the universe contains more than a critical amount of matter and energy, it curves back on itself like the surface of a sphere. Such a universe would be finite, but have no edges or boundaries. A sphere's surface has no center point on the surface itself. If the universe contains less than the critical density, it has negative curvature, like a saddle. This type of universe is infinite and will expand forever. Finally, if the density exactly equals the critical value, the universe is flat, following the rules of ordinary Euclidean geometry on cosmic scales. Current observations from satellites like Planck suggest we live in a flat universe, or very close to it. The density appears to be almost exactly at the critical value, but flat doesn't automatically mean infinite. The geometry tells us about the shape of space locally, but not necessarily about its global structure or topology. A flat universe could be infinite, stretching on forever like an endless plane. Or it could be finite with a complex topology that wraps around on itself. Imagine a torus, a donut shape. The surface of a torus is geometrically flat. Parallel lines stay parallel. Triangles have angles that sum to 180 degrees. Yet a torus has finite area and no edges. You could travel in what seems like a straight line and eventually return to where you started. The universe could have similar properties in 3 dimensions. It might seem to stretch forever, yet curve around and connect to itself in ways we can't directly perceive. Cosmologists have searched for evidence of such topology by looking for repeating patterns in the cosmic microwave background or matching galaxies on opposite sides of the sky. So far, they've found nothing convincing. We may never know if the universe is truly infinite. We can only observe a finite portion of it, the region from which light has had time to reach us. Beyond that horizon, the universe presumably continues, but we can never receive information from those regions. The observable part is likely tiny compared to the whole, which may extend forever in all directions. So does the universe have a center? According to everything we've observed and everything our best theories tell us, no. The Big Bang happened everywhere at once. Space is expanding uniformly in all directions. No location is special. No point can claim to be the cosmic middle. Every galaxy, every star, every atom exists at a place that was once compressed to infinite density at the moment of the Big Bang. That moment occurred at the same time everywhere, but it didn't occur at the same place because there was no place yet. Space itself came into existence in that moment. Understanding this requires letting go of our intuitive picture of the Big Bang as an explosion with a center. It demands we think about space not as a container that holds things, but as something that can grow, stretch, and evolve. The universe doesn't expand into anything. There's no pre-existing void it's filling. The expansion is the creation of new space between existing points. This leads to deeper questions about the nature of space itself. What is it made of? How can it expand? Where does new space come from? These questions push at the boundaries of our current understanding, hinting at physics we haven't yet fully grasped. But even without complete answers, we can say with confidence, the universe has no center in any meaningful sense. This isn't a limitation of our measurements or our telescopes. It's a fundamental feature of cosmic structure, woven into the very fabric of space and time, which raises an interesting point about humanity's place in the cosmos. Throughout history, we've had to abandon the idea that we occupy a special location. Ancient Greeks put Earth at the center of everything. Copernicus moved that center to the sun. Even into the 20th century, some believed the Milky Way was the entire universe, making it the cosmic center. Each time, we've discovered we're not as special as we thought. The realization that the universe has no center is perhaps the ultimate expression of this principle. Not only are we not at the center, but there is no center to be at. Every location is equally valid. Every observer sees the same uniform expansion. And yet, paradoxically, this means every location is special in its own way. The view from Earth is unique. The particular arrangement of galaxies we see, the specific cosmic history visible in our sky, exists nowhere else. An observer in a distant galaxy would see a different arrangement, a different set of cosmic neighbors. So while we're not at the center, we do occupy a unique vantage point in an infinite cosmos. Our observable universe, the sphere of space from which light has reached us, is ours alone. No other observer shares exactly the same view. This perspective shift transforms how we think about cosmic structure. You exist in a universe where your position is both ordinary and extraordinary. Ordinary because it follows the same physical laws as everywhere else. Extraordinary because the specific configuration of matter and energy visible from Earth exists nowhere else in the cosmos. But this raises a deeper question. If every location is equally valid, if there's no cosmic center, what determines the structure we actually see? The answer lies in something called the Cosmological Principle. First articulated formally in the 1930s, this principle makes a bold claim about reality itself. It states that on sufficiently large scales, the universe is both homogeneous and isotropic. Homogeneous means it has the same density everywhere. Isotropic means it looks the same in all directions. This isn't just mathematical convenience. It's a philosophical statement about the nature of existence. The part of the universe we can see represents a fair sample of the whole. The same physical laws apply throughout. No observer occupies a privileged position. These might sound like abstract concepts, but they have concrete observational consequences. If the universe truly has no center, we should see specific patterns in how matter distributes itself and how space expands. And we do. The cosmic microwave background provides the most dramatic evidence. This ancient light, released when the universe was just 380,000 years old, reaches us from all directions with remarkable uniformity. After accounting for our motion through space, the temperature varies by less than 1 part in 100,000 across the entire sky. Think about what this means. Light arriving from opposite sides of the observable universe, from regions that have never been in contact with each other, shows nearly identical properties. This uniformity isn't what you'd expect if the universe expanded from a central point. It's exactly what you'd predict if the Big Bang happened everywhere simultaneously. Galaxy surveys tell the same story. When astronomers map the distribution of galaxies across vast volumes of space, they find something remarkable. On small scales, galaxies cluster together. They form groups, clusters, and superclusters. But average over large enough volumes, about 260 megaparsecs or more, and the distribution becomes statistically uniform. No matter which direction you look, the large-scale structure appears the same. No preferred axis, no special direction, no hint of a center from which everything emanated. The expansion rate itself provides another crucial test. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, with more distant galaxies receding faster. The relationship is linear: double the distance, double the recession speed. At first glance, this seems to place us at the center of everything. After all, everything appears to be rushing away from Earth. But Hubble himself recognized this interpretation was wrong. Here's why. Imagine you're standing in a room where the floor is expanding uniformly in all directions. Every tile is getting bigger at the same rate. From your position, every other tile appears to be moving away. The farther away a tile is, the faster it seems to recede. Now imagine standing on a different tile. You'd see exactly the same pattern. Every tile moving away with speed proportional to distance. The expansion looks the same from every vantage point. This is precisely what happens with cosmic expansion. Every observer, regardless of location, would measure the same relationship between distance and recession speed. The expansion has no center because it's happening uniformly everywhere. But how can this be? How can space expand without expanding from somewhere? The key insight is that galaxies aren't moving through space. Space itself is expanding, carrying galaxies along with it. This distinction seems subtle, but it's fundamental to understanding why there's no center. Imagine drawing dots on a deflated balloon, then inflating it. The dots move apart, but they're not sliding across the rubber surface. The rubber itself is stretching, increasing the distance between dots. From any dot's perspective, all other dots appear to be moving away. The balloon's surface has no center. You can travel in any direction indefinitely without reaching an edge or finding a special point. Similarly, the three-dimensional fabric of space has no center point. Every region expands at the same rate. This expansion creates something that might seem paradoxical at first. While space is expanding everywhere, individual objects held together by fundamental forces don't expand. You're not getting bigger. Earth isn't expanding. Even the Milky Way maintains its size. Why not? Because electromagnetic forces binding atoms, gravity holding planets in orbit, and nuclear forces keeping atomic nuclei together are far stronger than the expansion of space on these scales. Only on truly cosmic scales, where distances between galaxy clusters span hundreds of millions of light years, does the expansion of space dominate over local forces. This means the expansion has a specific character. It's not that everything is rushing away from everything else through space. It's that new space is being created between distant objects. The fabric of reality itself is growing, and this fabric has no edge, no boundary, no center point. But wait, if the universe is expanding, doesn't it have to be expanding into something? Doesn't there have to be a region of space that existed before the expansion began? No. This is where our everyday intuitions completely fail us. The expansion isn't happening in some pre-existing void. Space itself is what's expanding. There's no outside for the universe to expand into, because outside doesn't exist. The universe is all there is. Asking what the universe is expanding into is like asking what's north of the North Pole. The question contains a hidden assumption that there's something beyond that simply doesn't apply. This connects to another common misconception. Many people imagine time before the Big Bang, a moment when the universe didn't exist, but space and time did. Again, this gets it backwards. According to our best current theories, Time itself began with the Big Bang. There is no before in any meaningful sense, because before is a temporal concept that only has meaning within time. The Big Bang wasn't an event that happened at a moment in time. It was the beginning of time itself. This has profound implications for the center question. If the Big Bang was the beginning of time, and it happened everywhere in space simultaneously, then every point in the current universe can trace its history back to that moment. Every location was present at the Big Bang. You're sitting right now at a point that existed at the very beginning of time. So is every other location in the cosmos. There's no special spot that can claim to be where it all started, because it all started everywhere. The mathematics behind this comes from Einstein's general relativity. His equations describe how matter and energy curve spacetime, and how that curvature affects the motion of objects. When applied to the universe as a whole, these equations yield several possible geometries. A universe with positive curvature would be like the surface of a sphere, finite in size, but without boundaries or edges. If you traveled far enough in one direction, you'd eventually return to your starting point. Such a universe would have no center for the same reason Earth's surface has no center. A universe with negative curvature would resemble a saddle shape, extending infinitely in all directions. This geometry also lacks a center. A flat universe, one with zero curvature, follows ordinary Euclidean geometry on cosmic scales. Parallel lines remain parallel. The angles of a triangle sum to exactly 180 degrees. This geometry could be either infinite or finite depending on the topology. Current observations strongly suggest our universe is flat or very close to it. Measurements of the cosmic microwave background, combined with observations of large-scale structure, indicate the density of the universe is extremely close to the critical value that produces flat geometry. But here's something that surprises many people. Even a flat universe doesn't necessarily have a center. If it's infinite, there's obviously no center to an infinite expanse. But even if it's finite, it could have a topology that wraps around on itself. Consider a torus, a donut shape. Its surface is geometrically flat. If you lived on a torus and measured angles and distances locally, you'd conclude space follows Euclidean geometry. Yet a torus has finite volume and no center point. You could travel in any direction and eventually return to your starting position without ever encountering an edge. The universe could have similar properties in 3 dimensions. It might be finite, yet unbounded, with no center and no edge. Cosmologists have searched for evidence of such topology by looking for repeating patterns in the cosmic microwave background, but so far have found nothing conclusive. This leaves us with a fascinating uncertainty. The universe might be infinite, extending forever in all directions. Or it might be finite with a complex topology we haven't yet detected. Either way, current observations show no sign of a center, but these observations have limits. We can only see a finite portion of the universe, the observable universe, roughly 46.5 billion light-years in radius. This is the region from which light has had time to reach us since the Big Bang. Beyond this horizon, the universe presumably continues. But we can never receive information from those regions. Light from beyond the observable horizon hasn't had time to reach us yet, and due to the accelerating expansion driven by dark energy, it may never reach us. This creates a profound limitation on knowledge itself. There could be structures beyond our cosmic horizon that we'll never detect. regions where the universe has different properties, perhaps even places where the cosmological principle breaks down. Some alternative cosmological models do allow for a universe with a center, known as Lemaitre-Tolman-Bondi models. These solutions to Einstein's equations describe spherically symmetric expanding universes. In principle, such a universe could have a preferred point. However, these models require abandoning the cosmological principle. They demand that we occupy a special location, that the universe looks different in different directions or from different positions. Current observations give no reason to adopt such models. The evidence consistently points toward homogeneity and isotropy on large scales. No preferred direction, no special location, no cosmic center. This brings us to a subtle but important point about what no center actually means. Physicists have examined several different ways you might define a center, and none apply to the universe. There's no center of rotation. Observations show no evidence the universe rotates as a whole. Without rotation, there's no axis to define a center. There's no center of curvature. The universe appears spatially flat on large scales, so there's no point around which space curves. Most importantly, there's no center of expansion. Despite the fact that distant galaxies are moving away from us, this doesn't indicate we're at a special location. Every observer sees the same pattern of expansion. This last point deserves emphasis because it's so counterintuitive. The expansion is uniform. Space stretches at the same rate everywhere. This means the expansion looks identical from every vantage point, which is only possible if there's no center from which it emanates. Think of it this way. In an explosion with a center, observers at different locations would see different patterns. Those near the center would see material rushing past them. Those far from the center would see everything moving in roughly the same direction away from the blast point. Cosmic expansion shows nothing like this. Every observer, regardless of position, sees everything moving away with velocities proportional to distance. This universal pattern is only consistent with centerless expansion. The implications are staggering. Not only does the universe lack a center, but this property is so fundamental it shapes our entire cosmic history. The Big Bang happened everywhere. The expansion proceeds everywhere. Structure formation occurs everywhere according to the same physical laws. You exist in a universe where every location participated equally in creation, where every point can legitimately claim to be the center because no point actually is, where the view from Earth is unique, yet follows the same patterns visible from any other galaxy. This cosmic democracy extends far deeper than you might think. Understanding why requires exploring the actual geometry of space itself. Most people learn geometry from flat surfaces, paper, chalkboards, screens. In Euclidean geometry, parallel lines never meet. Triangles have angles summing to exactly 180 degrees, and the shortest distance between points is always a straight line. This works perfectly for everyday life. But the universe isn't bound by Euclidean rules. Einstein revealed that massive objects warp the fabric of spacetime. Near Earth, this curvature is subtle. Near a black hole, it's extreme. But what about the universe as a whole? Does space curve back on itself like the surface of a sphere? Does it stretch infinitely like an endless plane? Or does it bend in stranger ways we struggle to visualize? Three possibilities emerge from the equations. If the average density of the universe exceeds a critical threshold, space curves positively like a sphere's surface. Walk far enough in one direction, and you'd eventually return to your starting point. Such a universe would be finite yet boundless, containing a limited amount of space with no edge. If density falls below that critical value, space curves negatively like a saddle. This universe extends infinitely, forever expanding into endless possibility. If density hits the critical value exactly, space is perfectly flat, obeying Euclidean geometry on cosmic scales. Observations point decisively toward the third option. The Planck satellite measured the cosmic microwave background with extraordinary precision, finding that the universe's geometry is flat to within a tiny margin of error. Space appears to follow Euclidean rules when averaged across cosmic distances. But here's where it gets interesting. Flat doesn't necessarily mean infinite. The geometry of space is separate from its topology, the way space connects to itself. Consider a piece of paper. Flat geometry, clearly. Now roll it into a cylinder. Still flat from the perspective of someone confined to the surface, yet now it loops back on itself in one direction. Roll it further into a torus, a donut shape. The surface remains geometrically flat. Parallel lines stay parallel. Triangles behave as expected, yet the space is finite, wrapping around to meet itself. The universe could work the same way. Even with perfectly flat geometry, space might curve back on itself through dimensions we can't directly perceive. Travel far enough in one direction, and you might return to where you started, not because space curves, but because it connects to itself in unexpected ways. Cosmologists have searched for evidence of such topology. If the universe wraps around, we should see repeating patterns in the cosmic microwave background, the same structures appearing on opposite sides of the sky, matched sets of galaxies in different directions. So far, these searches have found nothing convincing. Either the universe doesn't loop back on itself, or it's so vast that the repetition scale exceeds our observable horizon. This brings us to the profound question of infinity itself. If the universe is flat or negatively curved and doesn't loop back topologically, then it extends infinitely, not just really big, not just unimaginably vast, actually infinite, containing infinite space, infinite matter, infinite energy, infinite galaxies. The implications stagger the mind. An infinite universe means infinite possibilities play out somewhere. Every physically possible arrangement of matter exists not just once, but infinitely many times. There are infinite Earth-like planets, infinite civilizations, infinite versions of you making different choices. But we may never know for certain whether infinity is real. We can only observe a finite portion of the universe, the region from which light has had time to reach us. Beyond that boundary, the cosmos continues, but we're fundamentally cut off from information about it. Our observable bubble might be minuscule compared to the whole, or it might represent a substantial fraction. We have no way to tell. Even if we could somehow prove the universe is flat, that wouldn't settle whether it's infinite or finite with complex topology. The question might remain forever beyond empirical resolution, trapped in the realm of mathematical possibility rather than observational certainty. This uncertainty connects to something deeper about the nature of knowledge itself. Science relies on observation, on testing predictions against reality. But some questions push against the boundaries of what's observable in principle, not just in practice. The universe's total size, whether infinity exists, what lies beyond our cosmic horizon. These may be questions we can reason about, but never definitively answer. Yet even within these limitations, we've learned something profound. Whether the universe is finite or infinite, it has no center. The balloon analogy helps visualize this, though like all analogies, it has limits. Picture a balloon's surface as space itself, not the rubber as a three-dimensional object, but purely the two-dimensional surface. Dots on this surface represent galaxies. As you inflate the balloon, the surface stretches. Every dot moves away from every other dot, but the dots themselves stay in place on the surface. The rubber between them expands. Now ask, where's the center of the balloon's surface? There isn't one. You might point to the center of the balloon as a three-dimensional object, but that point isn't on the surface. It exists in a direction unavailable to creatures confined to the surface. For them, the surface has no center. Every point is equivalent to every other. The universe works similarly, except with an extra dimension. We're confined to three-dimensional space, which may curve through higher dimensions we can't access. The Big Bang might be like the balloon's center, not a place in space, but a direction in time, or in dimensions beyond our perception. As the universe expands, we can run time backward, watching galaxies converge. Keep going, and you reach the Big Bang, when everything was compressed to extraordinary density. But this moment occurred everywhere simultaneously. There's no location you can point to and say the Big Bang happened there. It happened where you're sitting. It happened in the most distant galaxy. It happened uniformly throughout all of space. This is why the cosmic microwave background arrives from all directions equally. We're not seeing radiation from a distant point where the Big Bang occurred. We're seeing the afterglow from every point in space, from a time when the universe was hot and dense everywhere. The expansion itself reinforces this centerless nature. Space doesn't expand outward from some origin point. It expands equally in all regions. Every cubic meter of space grows at the same rate, creating more space between distant objects. This uniform expansion is only consistent with a universe that has no preferred location. Some find this disturbing. We're pattern-seeking creatures who naturally look for special points, origins, centers of importance. The idea that no location is special challenges deep intuitions about how reality should work. But there's beauty in this cosmic democracy too. It means the laws of physics operate the same way everywhere. The chemistry that enables life on Earth works identically in galaxies billions of light years away. The fundamental constants that govern particle interactions don't vary from place to place. We can trust that our observations reflect universal principles rather than local quirks. This uniformity also means observers anywhere in the universe see roughly the same large-scale patterns we do. An astronomer in a galaxy at the edge of our observable universe would see galaxies distributed around them in all directions, would measure the same expansion rate, would detect the same cosmic microwave background temperature. The view from Earth isn't special, but neither is it misleading. What we observe from our location genuinely reflects cosmic truth rather than provincial perspective. Understanding this required humanity to repeatedly abandon cherished assumptions about our cosmic significance. Ancient Greeks placed Earth at the center of everything. Copernicus displaced us from that position, placing the Sun at the center instead. Later observations revealed the Sun as just one ordinary star among billions in the Milky Way. Then we discovered the Milky Way was just one galaxy among billions. Each step removed us further from any claim to cosmic centrality. And now we know even the concept of centrality doesn't apply. There's no cosmic center to occupy or be displaced from. This progression reflects something important about how science works. We begin with intuitive assumptions based on limited observations. Earth seems stationary, so we assume it is. Everything appears to revolve around us, so we construct models placing us at the center. These models work reasonably well for local phenomena, but fail when extended to larger scales. Better observations force us to revise our assumptions, often in counterintuitive directions. The revisions initially meet resistance because they conflict with deep-seated intuitions. But eventually, the evidence becomes overwhelming, and the new understanding becomes the foundation for further discovery. We're now at a stage where our observations reach cosmic scales. We map the universe's large-scale structure, measure its expansion history, probe its geometry, and consistently, the data points toward homogeneity and isotropy. No preferred direction, no special location, no cosmic center. This conclusion isn't just observational. It flows from the same theoretical framework that's been tested extensively in other contexts. General relativity describes gravity as the curvature of spacetime. Applied to the universe as a whole, it produces models where space can expand uniformly without a center. These models match observations so precisely that abandoning them would require explaining away vast amounts of consistent evidence. Could we be wrong? Could future observations reveal inhomogeneities or preferred directions that current measurements miss? In principle, yes. Science remains open to revision when confronted with new evidence, but the evidence would need to be compelling, explaining not just new observations, but also why previous measurements appeared so uniform. The alternative models that allow for a cosmic center exist mathematically. Lemaitre-Tolman-Bondi solutions describe spherically symmetric universes that could have a preferred point. But applying these models to our universe requires abandoning the cosmological principle, assuming we occupy a special location that happens to make the universe appear homogeneous and isotropic. This violates a principle that served science well for centuries. When faced with observations that could be explained either by universal laws operating everywhere or by coincidentally special circumstances at our location, the universal explanation has consistently proven correct. The Sun isn't special among stars. Earth isn't special among planets. The Milky Way isn't special among galaxies. Assuming our location is cosmically special would reverse this successful pattern without observational justification. So we're left with a universe that has no center, because centeredness itself is meaningless in a space that's homogeneous and isotropic on large scales. Every location participated equally in the Big Bang. Every region expands at the same rate. Every observer sees similar patterns. You're not at the center of the universe, but neither is anyone else. The universe's centerlessness isn't just an abstract theoretical claim. We can test it, measure it, map it. Start with galaxy surveys. Astronomers catalog millions of galaxies across vast swaths of sky, measuring their positions and distances. Plot these on a three-dimensional map. What pattern emerges? At small scales, galaxies cluster together. Gravity pulls them into groups, clusters, superclusters. These structures form filaments and sheets surrounding enormous voids, the cosmic web. But zoom out further, average over larger and larger volumes. the lumpiness smooths out. By the time you're examining regions hundreds of millions of light years across, the distribution becomes remarkably uniform. No matter which direction you look, you find roughly the same density of galaxies. This homogeneity holds across observable scales. Simulations suggest the distribution becomes statistically homogeneous when averaged over regions about 260 megaparsecs or larger. That's roughly 850 million light-years. Beyond this scale, the universe looks essentially the same everywhere. No dense concentrations that might mark a center. No voids that suggest we're on the edge. Just cosmic uniformity. Then there's the cosmic microwave background. This radiation, released when the universe became transparent about 380,000 years after the Big Bang, provides our deepest view into cosmic history. Satellites like COBE, WMAP, and Planck have mapped this radiation across the entire sky with extraordinary precision. The result? Near-perfect uniformity. Temperature variations exist, but they're tiny, about 1 part in 100,000. These fluctuations represent density variations in the early universe, seeds that grew into today's galaxies. But the crucial point is their distribution. They appear randomly scattered across the sky with no preferred direction or location. If the Big Bang had a center, if expansion radiated from some point, we'd expect to see patterns in this radiation. Hotter or denser regions pointing toward that center. We see nothing of the kind. The CMB tells another story too. Its temperature spectrum matches a blackbody curve almost perfectly, indicating it came from a time when the entire observable universe was in thermal equilibrium. Every region had communicated with every other region, reaching the same temperature. This only makes sense if all these regions originated from the same initial conditions everywhere, not from some localized explosion expanding outward. What about the expansion itself? Hubble's law provides another test. If galaxies recede from us with velocities proportional to distance, and this relationship holds in all directions, then either we're at the center of expansion, or there is no center. Observations decisively favor the second option. Measure the expansion rate in different directions: northeast, southwest, up, down. It's the same everywhere. The Hubble constant doesn't vary with direction. This isotropy combined with large-scale homogeneity leaves no room for a special central point. But here's where it gets interesting. What if we're wrong about homogeneity? What if the universe only appears uniform within our observable region, but varies dramatically beyond? This possibility exists mathematically. Lemaitre-Tolman-Bondy models describe universes with spherical symmetry around a central point. In these models, density varies with distance from center. You could construct a model where we happen to live near the center of a giant spherically symmetric bubble. From our perspective, the universe would look homogeneous and isotropic, even though it actually has a preferred point. Why don't cosmologists favor these models? Several reasons. First, they require giving up the cosmological principle, the assumption that we don't occupy a special location. This principle has served science well. Every time we've assumed our position was ordinary rather than special, we've been proven right. Earth isn't the center of the solar system. The Sun isn't the center of the galaxy. The Milky Way isn't the center of the universe. Abandoning this principle now seems like taking several steps backward. Second, these centered models need fine-tuning. To make the universe appear as homogeneous as we observe from a non-central location requires carefully adjusting the density profile. It's possible, but contrived. The standard centerless models achieve the same observational fit naturally, without special adjustments. Third, and most importantly, we have no observational evidence requiring centered models. Everything we measure fits the simpler, homogeneous, isotropic models perfectly. Why complicate the theory without empirical justification? Still, the possibility haunts cosmology. We can only observe a finite region. The observable universe extends about 46.5 billion light-years in all directions, limited by the finite speed of light and the universe's finite age. Beyond this horizon, the universe continues. We just can't see it. What happens out there? If the cosmological principle holds everywhere, then regions beyond our horizon look like regions within it. More galaxies, more clusters, more cosmic web, all arranged in the same statistically homogeneous pattern, extending infinitely in all directions. No center anywhere. But we can't verify this directly. Those distant regions remain forever beyond our observational reach, not just practically beyond our current technology, but fundamentally beyond what's physically possible to observe. Light from regions far enough away will never reach us because cosmic expansion carries them away faster than light can traverse the growing distance between us. This limitation raises profound questions about scientific knowledge. Can we claim the universe has no center if we can only observe a finite portion? How much confidence should we place in extrapolating local observations to cosmic scales? Physicists argue the extrapolation is justified by consistency. The laws of physics that govern our local region also explain observations from distant regions billions of light-years away. Stellar physics works the same in distant galaxies. Nuclear reactions proceed identically. Gravity behaves as Einstein's equations predict across cosmic scales. This consistency suggests the same laws operate everywhere, supporting the cosmological principle's claim that the universe is fundamentally the same throughout. Moreover, the centerless model makes specific predictions that have been tested and confirmed. It predicts the relationship between galaxy distance and recession velocity. Confirmed. It predicts the temperature and spectrum of the cosmic microwave background. Confirmed. It predicts the abundances of light elements formed in the early universe. Confirmed. These successes build confidence that the model captures something real about cosmic structure, yet certainty remains elusive. The question of whether the universe is finite or infinite connects directly to the center question. If the universe is infinite, there's no center by definition. You can't identify a middle point in infinite space. But if it's finite, here the geometry becomes crucial. A finite universe doesn't necessarily have a center. Consider Earth's surface. Finite area, no edges, no center. You can walk in any direction indefinitely without reaching a boundary or privileged point. The surface is two-dimensional, curved into a sphere in three-dimensional space. But creatures confined to the surface, unable to perceive the third dimension, would experience a finite space without center. Similarly, our three-dimensional universe could be curved into a four-dimensional shape. A hypersphere, perhaps, finite in volume, but without boundaries or center when viewed from within. We wouldn't perceive the fourth dimension directly, just as flatlanders on a sphere don't perceive the dimension perpendicular to their surface. but we'd experience the consequences. A finite universe we could traverse endlessly without finding edges. Alternatively, even a flat universe could be finite through topological tricks. Imagine space wraps around on itself like a torus. Travel far enough in one direction, and you'd eventually return to your starting point from the opposite direction. This creates a finite volume from flat geometry through connectivity rather than curvature. Cosmologists have searched for evidence of such topology. If space wraps around, we might see the same galaxies in multiple directions, light having traveled different paths around the universe to reach us. Or we might find matching patterns in opposite regions of the cosmic microwave background. So far, searchers have found nothing. Either the universe is too large for these effects to show up within our observable region, or space doesn't wrap around. Current observations favor flatness. The universe's geometry appears Euclidean on large scales. Parallel lines stay parallel. Triangles' angles sum to 180 degrees. Data from the Planck satellite indicates the universe is flat to within measurement uncertainty. This flatness doesn't determine whether space is infinite or finite. Both remain possibilities consistent with observations. If the universe is infinite, fascinating consequences follow. Infinite space means infinite matter and energy, assuming average density stays constant. Infinitely many galaxies, infinitely many stars, infinitely many planets. And if the conditions that produced life on Earth aren't unique, then infinitely many planets with life, infinitely many civilizations, infinitely many observers asking whether the universe has a center. More strangely, an infinite universe with finite matter density might contain infinite copies of you. With infinite space and finite possible arrangements of particles, every possible configuration must repeat infinitely often. Somewhere in the infinite cosmos, there's another Earth, identical to ours, down to the last atom. Another you, reading these exact words at this exact moment. In fact, infinitely many such copies. This isn't mysticism. It's a straightforward consequence of infinity and finite possibilities. But it remains speculative because we can't observe these distant duplicates. They lie far beyond our cosmic horizon, forever inaccessible. Whether finite or infinite, whether flat or curved, the universe's structure consistently points away from having a center. Every model that fits observations describes space where no location is privileged, where cosmic properties remain the same across vast distances, where expansion occurs uniformly without a preferred point. This centerlessness reflects something deep about how the universe works. It's not an accident of current structure, but a fundamental feature built into cosmic evolution from the beginning. The Big Bang didn't happen at a point, it happened everywhere. Expansion doesn't radiate from somewhere, it occurs at all locations simultaneously. The universe doesn't have a center, because the very concept of cosmic centrality is meaningless in a homogeneous, isotropic space. Understanding this requires abandoning intuitions built from everyday experience. We're accustomed to things having centers. Cities have downtowns, countries have capitals, explosions have epicenters. But the universe operates differently. It's not an object situated in space, it is space. And space itself, the stage on which cosmic events unfold, has no inherent center point. This realization completes a journey that began centuries ago when humans first questioned whether Earth sat at the cosmos's center. The answer, repeatedly refined by better observations, and deeper understanding consistently points the same direction. Not only is Earth not central, neither is anything else. Centrality itself doesn't apply. The universe has no middle because it has no structure that would define one. Yet this cosmic democracy raises profound questions about observation itself. Every point appears central from its own perspective, but what does that actually mean for how we investigate the universe? When astronomers study the cosmos, they're not passive observers recording objective truth. They're participants embedded within the system they're examining. Their location determines what they can see. Their motion affects measurements. Their moment in cosmic history limits accessible information. This creates a peculiar challenge. We can't step outside the universe to examine it from a neutral vantage point. We're stuck inside, peering outward from one particular location at one particular time. How can we determine whether the universe truly lacks a center, or whether we simply haven't detected it yet? The answer comes from testing predictions. If the universe genuinely has no center, certain patterns should emerge in observations. Matter distribution should appear roughly uniform across large enough volumes. Expansion should look the same in all directions. The cosmic microwave background should show no preferred orientation. Physical laws should operate identically everywhere we can observe. These predictions can be tested, and they have been repeatedly with increasing precision. Start with galaxy surveys. Astronomers map millions of galaxies, recording their positions and distances. Initially, the distribution looks clumpy. Galaxies cluster together. Clusters group into superclusters. Vast filaments stretch across space while enormous voids contain almost nothing. But average over larger volumes, and the picture changes. The clumpiness smooths out. Statistical properties become uniform. By scales of several 100 million light-years, the universe appears homogeneous. No matter which direction you look, given sufficient volume, you find roughly the same density of galaxies. This homogeneity extends to cosmic expansion. Hubble's law states that recession velocity increases with distance. Galaxies twice as far away recede twice as fast. This relationship holds in all directions with remarkable consistency. If the universe had a center, we'd expect deviations. Galaxies in the direction toward the center should behave differently than those in the opposite direction. We'd see asymmetries in expansion rates, but we don't. The pattern remains uniform across the sky. The cosmic microwave background provides even stronger evidence. This radiation, the oldest light we can observe, shows temperature variations of only about 1 part in 100,000. The universe, when it became transparent, was extraordinarily uniform. More importantly, these tiny temperature fluctuations show no large-scale asymmetry. They're distributed evenly across all directions. There's no hotspot that might indicate proximity to some cosmic origin point. No cold region suggesting distance from a center. Detailed analysis of the CMB measures cosmological parameters with stunning precision. The universe's age, density, composition, and geometry all emerge from this ancient light. And every measurement supports the picture of a centerless cosmos. But what about those alternative models mentioned in theoretical papers? The Lemaitre-Tolman-Bondi solutions that allow for spherical symmetry and thus a potential center. These models remain mathematically valid solutions to Einstein's equations. They describe universes that could have centers while still expanding. In such a universe, we might happen to live near the center, which would explain why expansion appears uniform from our perspective. However, these models require abandoning the cosmological principle. They propose that our location is special, that the universe looks the same in all directions from here, specifically because we're centrally positioned. Other observers at different locations would see different patterns. This requires extraordinary evidence. Carl Sagan's dictum applies: extraordinary claims demand extraordinary proof. Proposing that our location is cosmically special reverses centuries of scientific progress that consistently displaced humanity from privileged positions. Moreover, LTB models make predictions that can be tested. They should produce specific signatures in galaxy distributions, in the CMB, in how expansion varies with direction. Searches for these signatures have found nothing. Observations continue supporting standard cosmology, where no location is special. The scientific community therefore favors models without centers, not from philosophical preference, but from empirical evidence. Every test supports homogeneity and isotropy. No observation requires introducing a cosmic center. This doesn't absolutely prove the universe lacks a center beyond our observable region. Perhaps it has some complex structure too large for us to detect. But this possibility retreats further, with each observation confirming uniformity at ever larger scales. There's another way to think about centers that might seem relevant. Mass centers, the points around which systems balance. Our solar system has a center of mass. Galaxies have centers of mass. Do these somehow combine into a cosmic center? No. Here's why. In a finite bounded system, you can calculate a center of mass by averaging all positions weighted by their masses. The solar system works this way. The Sun contains most mass, so the center of mass sits near the Sun's core. But this only works for systems with boundaries, with a finite amount of matter in a defined region. The universe, whether infinite or finite without edges, doesn't qualify. In an infinite universe, there's no way to calculate a center of mass. You can't average infinite positions. The concept simply doesn't apply. It's like asking what's the average value of all integers. The question has no meaningful answer. Even in a finite universe without boundaries, like the surface of a sphere, there's no center within the space itself. A sphere's surface has no point that could serve as a center of mass for objects distributed across it. The geometric center of the sphere exists in a different dimension, not accessible to creatures confined to the surface. What about rotation? Could the universe spin around some axis, defining a center that way? Current observations find no evidence for cosmic rotation. The universe appears to expand but not rotate. Studies of galaxy orientations, CMB patterns, and large-scale structure all indicate no preferred axis of spin. If the universe rotated, frame-dragging effects predicted by general relativity would create detectable signatures. We'd see systematic alignments in galaxy angular momenta. The CMB would show characteristic patterns. None of these appear in data. Without rotation, there's no rotational center. Without expansion from a point, there's no expansion center. Without a geometric center in space's topology, there's no positional center. Every traditional definition of center fails to apply. This brings us to perhaps the deepest question. Why does the universe have this property? Why is space structured such that no location is special? The honest answer is we don't fully know. The cosmological principle provides a framework for understanding observations, but it doesn't explain why the principle holds. Why should the universe be homogeneous and isotropic? Why not lumpy, asymmetric, with clear preferred locations? One possibility involves quantum fluctuations in the early universe. During cosmic inflation, quantum variations got stretched to astronomical scales. These variations were random, showing no preferred direction or location. They seeded galaxy formation, creating the large-scale structure we observe. If this picture is correct, the universe's uniformity traces back to the random nature of quantum mechanics. There was no mechanism to create special locations because the underlying quantum fluctuations treated all points equivalently. Another consideration comes from the anthropic principle. If the universe varied dramatically across different regions, with some areas far denser or hotter than others, life might only emerge in specific locations. We necessarily find ourselves in a region compatible with life. But this doesn't explain why the observable universe appears uniform across scales far larger than necessary for life. The anthropic principle might explain finding ourselves in a habitable region, but not why that region extends billions of light years in all directions with consistent properties. Perhaps the deepest answer is that space itself has no inherent structure to define centers. Space isn't a thing with properties like objects we encounter. It's the framework within which things exist. Asking where space's center is might be like asking what color mathematics is. A category error applying concepts from one domain inappropriately to another. General relativity treats spacetime as a dynamic entity that curves and bends in response to matter and energy. But this curvature itself has no preferred location. Einstein's equations describe how mass-energy curves spacetime, but they don't privilege any particular point. Solutions to these equations that match observations all describe universes without centers. The mathematics itself points away from cosmic centrality. This mathematical structure might reflect something fundamental about physical law, the principle that physics operates the same way everywhere, that no location is privileged, connects to deep symmetries in nature. Emmy Noether proved that symmetries in physical laws correspond to conservation principles. Symmetry in time gives energy conservation. Symmetry in space gives momentum conservation. Symmetry under rotations gives angular momentum conservation. The universe's homogeneity represents a symmetry. Physics doesn't change when you move from one location to another. This symmetry might be as fundamental as the others, built into the basic structure of physical law. If true, the universe couldn't have a center without violating these deep symmetries. The centerlessness isn't accidental, but required by the fundamental architecture of reality. This perspective transforms the question. Instead of asking, why doesn't the universe have a center? We might ask, what would it even mean for the universe to have a center given the symmetries of physical law? The answer increasingly appears to be, it wouldn't mean anything. The concept doesn't fit the framework. Like asking for the temperature of justice or the weight of Tuesday, we're applying a concept beyond its valid domain. Yet this conclusion, while intellectually satisfying to physicists, often feels unsatisfying intuitively. Our everyday experience so strongly suggests that things should have centers that abandoning the concept for the universe feels wrong. This tension between intuition and reality recurs throughout physics. Quantum mechanics violates intuitions about particles having definite positions. Relativity violates intuitions about absolute time. Now, cosmology violates intuitions about cosmic centrality. Each violation teaches the same lesson. The universe doesn't conform to human intuition. Our brains evolved to navigate medium-sized objects at moderate speeds in Earth's gravity. They didn't evolve to intuitively grasp quantum mechanics, relativistic effects, or cosmic scale structure. Science succeeds by developing mathematics and observations that extend beyond intuition. The equations work even when they feel wrong. The observations remain even when they contradict expectations. This is where we stand with cosmic centerlessness. The math says no center. The observations confirm no center. Intuition protests, but intuition isn't a reliable guide at these scales. Understanding this requires accepting that the universe operates differently than everyday objects. It's not just bigger than a planet or solar system, it's categorically different. The rules change, new principles apply. Human history shows our cosmic perspective expanding through stages. First, we thought Earth was everything. Then we realized Earth orbits the Sun. Then we discovered the Sun is one star among billions in a galaxy. Then we found billions of galaxies filling space. Each expansion humbled our cosmic significance. Each revealed we're less central, less special, less unique than previously believed. The realization that the universe has no center represents perhaps the final step in this journey. Not only are we not at the center, there is no center to be at. The very concept doesn't apply. This completes the Copernican revolution. Copernicus removed Earth from the cosmic center. Modern cosmology removed the concept of cosmic centrality altogether. Where does this leave us? Floating in a centerless cosmos, with no special location, no privileged perspective, no unique position from which to view reality. Yet paradoxically, this makes every location special in its own way. If no point is privileged, then all points are equal. Your location, wherever you are, has the same cosmic status as any other. You're exactly as central as anyone else, which is to say, not central at all, which is to say, perfectly positioned to observe the universe from your unique vantage point. This democratic cosmos removes hierarchy, but preserves meaning. The universe's structure doesn't privilege any observer, but every observer gets their own equally valid perspective on cosmic truth. The profound realization that we're nowhere special comes with an unexpected consequence. If there's no center, then navigation through the cosmos operates by entirely different rules than we might imagine. Consider how we navigate on Earth. Every direction has meaning relative to landmarks, poles, or centers of reference. North leads to the Arctic. Down points toward Earth's core. Every journey has a starting point and destination defined by their relationship to these references. The universe offers no such convenience. An astronaut traveling between galaxies couldn't use cardinal directions. There's no cosmic north, no universal up or down. Direction only has meaning relative to where you started or where you're going. The universe provides no absolute coordinate system, no grid painted on space itself. This relativity of position extends beyond navigation. It fundamentally shapes how we understand cosmic events. When astronomers observe a distant supernova, they can't describe its location relative to some cosmic origin point. They can only specify its position relative to Earth, or to the galaxy it inhabits, or to nearby clusters. Every location depends on your reference frame, but here's where it gets stranger. Because space itself expands, even relative positions shift over time. A galaxy 100 million light-years away today will be farther tomorrow. Not because it moved through space, but because the space between us grew. Distance becomes a moving target. This expanding space creates puzzles about what now even means across cosmic scales. When we observe a distant galaxy, we see it as it was billions of years ago when its light began traveling to us. What's happening in that galaxy right now, at this exact moment? The question seems simple, but has no meaningful answer. Relativity tells us simultaneity depends on reference frame. Events that appear simultaneous from Earth might not be simultaneous from another galaxy. There's no universal clock ticking away the same moment everywhere. Time, like space, refuses to provide the absolute framework our intuition demands. These complications emerge directly from centerlessness. With no privileged reference point, no cosmic clock, no absolute grid, every measurement becomes relative. The universe operates more like relationships between objects than objects existing on a fixed stage. Think about what this means for cosmic history. The Big Bang didn't happen at a location, it happened at a time. Every point in space participated simultaneously. If you trace any particle's history backward, you eventually reach that moment when all of space was compressed to inconceivable density. But compressed compared to what? There was no outside space to compress into. Space itself was that dense state. The Big Bang was the beginning of space, not an event within space. This distinction, while grammatically simple, represents one of the hardest concepts in cosmology to truly internalize. People often ask what the universe is expanding into. The question assumes there's something beyond the universe, some larger space that contains it. But if the universe is all of space, there's nothing outside to expand into. Space doesn't expand into anything, it just expands. Period. This creates a curious situation where the universe can be finite yet unbounded. Imagine walking in a straight line across the surface of Earth. You'd eventually return to your starting point without ever hitting an edge or boundary. The surface is finite in area but has no edge. Space might work similarly in 3 dimensions. A finite but unbounded universe could be shaped like a 3-dimensional analog of a torus, a donut shape. Travel far enough in any direction and you'd eventually loop back to where you started. The journey might take hundreds of billions of years even at light speed, but mathematically it's possible. Such a universe would still have no center. Just as the surface of a torus has no privileged point, a toroidal universe offers no special location. Every point looks the same as every other point. The topology wraps around on itself in a way that prevents any point from being central. Cosmologists have searched for evidence of such topology by looking for repeating patterns in the cosmic microwave background. If space loops back on itself on scales smaller than the observable universe, we might see the same structures repeated in different directions, like seeing the back of your own head in a hall of mirrors. So far, no such repetition has been found. The observable universe appears consistent with either an infinite flat space or a finite space so large that it loops back beyond our cosmic horizon. We can't tell which because we can't see far enough. This observational limit represents a fundamental boundary to knowledge. Light from beyond the cosmic horizon hasn't had time to reach us yet. As the universe ages, that horizon expands and we can see farther. But cosmic expansion works against us. Dark energy accelerates expansion. Distant regions recede faster and faster. Eventually, galaxies beyond a certain distance recede so quickly that their light never reaches us, even given infinite time. A cosmic event horizon forms, similar to the event horizon around a black hole. Beyond this event horizon, the universe continues. Galaxies form, stars shine, perhaps civilizations arise. But we can never observe them. They're causally disconnected from us forever. Information from those regions can never reach our location. This creates an unsettling realization. Most of the universe remains forever beyond our knowledge. We inhabit a cosmic bubble of observability, surrounded by an infinite expanse we can never see. The universe's structure beyond that boundary remains speculative. Does the cosmological principle hold everywhere? Is space homogeneous and isotropic throughout the entire cosmos, or just within our observable patch? We assume the same physical laws apply everywhere, but we can't verify this assumption beyond what we observe. Alternative models do exist, where the universe has large-scale structures violating homogeneity. The Lemaitre-Tolman-Bondi models describe universes with spherical symmetry and potentially a center. These models remain mathematically valid solutions to Einstein's equations. However, these alternatives require abandoning the cosmological principle. They suggest our observable universe might be a special region within a larger inhomogeneous cosmos. We'd be back to occupying a privileged position, contradicting centuries of cosmological humility. No observational evidence supports these models. Every test of large-scale structure confirms homogeneity and isotropy within measurement limits. The simplest explanation remains that what we observe locally reflects universal structure everywhere. Occam's razor favors the centerless universe. Why postulate complex hierarchies of structure when simple homogeneity explains all observations? Special positions require special explanations. Generic positions need only generic principles. This philosophical preference for simplicity has proven remarkably successful in physics. The laws governing Earth apply throughout the solar system. The laws governing our solar system apply throughout the galaxy. The laws governing our galaxy appear to apply throughout the observable universe. Extrapolating this pattern suggests physical laws apply throughout the entire cosmos, observed or not. The universe operates by consistent rules everywhere, with no special locations requiring different physics. This universality makes cosmology possible. Without it, we'd be stuck describing only what we directly observe with no ability to generalize. Science requires assuming nature's laws apply beyond immediate experience. The centerless universe embodies this assumption at the largest scale. But assumptions, no matter how reasonable, remain assumptions until tested. The true structure of the universe beyond our horizon remains unknown. We believe it continues homogeneously because that's the simplest extension of what we see, not because we've proven it. This uncertainty doesn't undermine cosmology. All science works with incomplete information, building models that explain observations while remaining open to revision. The centerless universe represents our best current understanding, not absolute truth. Future observations might change this picture. Perhaps we'll detect patterns in the cosmic microwave background suggesting finite topology. Maybe gravitational wave astronomy will reveal large-scale structures inconsistent with perfect homogeneity. Science adjusts to new evidence. For now, though, every test confirms the same story. No center of rotation, no center of mass, no center of curvature, no center of expansion. The universe stubbornly refuses to provide any kind of central reference point. This consistency across independent tests strengthens confidence in the conclusion. When multiple measurement methods all point the same direction, the result likely reflects reality rather than systematic error. The cosmic microwave background appears uniform from all directions to 1 part in 100,000. Galaxy surveys show homogeneous distribution on scales above 260 megaparsecs. Supernovae measurements confirm uniform expansion. Everything fits the centerless model. Yet the human mind keeps returning to the question, surely there must be some special point, some origin, some location where it all began. The intuition runs deep that explosions have centers, that expansion implies a starting point. Breaking free from this intuition requires recognizing its source. Our experience with explosions comes from events within space, where material expands from a point into surrounding space. The Big Bang was an explosion of space itself, a categorically different phenomenon. No ordinary explosion created the universe. No bomb went off at some location. No force pushed matter outward from a center. Instead, space itself began expanding, carrying matter along for the ride. The expansion has no center because every point participates equally. This equality of all points represents the final demolition of cosmic hierarchy. Ancient cosmologies placed Earth at the center. Copernicus displaced us to orbit the Sun. Hubble showed our galaxy as one among billions. Now we learn even the concept of centrality doesn't apply. The journey from geocentrism to cosmic democracy took centuries. Each step met resistance because each contradicted intuition and deflated human cosmic importance. The centerless universe completes this progression. Where does this leave us in the grand scheme? Nowhere special, somewhere random, exactly where we should expect to find ourselves in a universe without preferred locations. Our position holds no cosmic significance beyond the fact that we're here to observe it. This might seem depressing. We're not special, not central, not positioned at any meaningful location. But flip the perspective. Being nowhere special means everywhere is equally valid. Your observation point has the same cosmic status as any other. The universe's structure doesn't privilege any observer. Every consciousness that arises anywhere in the cosmos gets their own unique but equally valid perspective. The view from Earth matters just as much as the view from any distant galaxy. This democratic cosmos removes hierarchy without removing meaning. You matter because you observe, not because of where you observe from. The philosophical implications run deeper still. A universe without center challenges our fundamental categories of thought. Direction loses absolute meaning. Up and down exist only relative to local gravity. Forward and backward depend entirely on your chosen reference frame. Consider asking someone in deep space which direction is up. The question reveals itself as nonsense. No universal up exists. Only local definitions relative to nearby massive objects. The same applies to cosmic location. Asking where the universe's center lies commits the same error, imposing a local concept onto something that transcends locality itself. This cosmic democracy extends beyond mere position. Physical laws appear identical everywhere we can observe. Gravity works the same in distant galaxies as in our solar system. Light travels at constant speed throughout the cosmos. Quantum mechanics governs atoms here exactly as it governs atoms billions of light years away. Scientists call this the cosmological principle, the assumption that the universe looks roughly the same from all vantage points when viewed on sufficiently large scales. Not just that it has no center, but that it has no special locations whatsoever. Every position is equivalent to every other position. The evidence supporting this principle continues accumulating. Galaxy surveys mapping hundreds of millions of galaxies find statistical uniformity on the largest scales. The cosmic microwave background shows temperature variations of only 1 part in 100,000 across the entire sky. Type 1. A supernovae at varying distances all indicate uniform expansion. Yet the cosmological principle remains an assumption, not a proven fact. We can only observe the universe from one location, Earth. We can't actually visit distant galaxies to verify they see what we predict they should see. Alternative models exist where the universe does have structure on scales larger than we can observe. Lemaitre-Tolman-Bondi models, for instance, describe universes with spherical symmetry around a central point. These solutions to Einstein's equations are mathematically valid. They could, in principle, describe reality. If the observable universe represents a tiny fraction of the whole, we might live near the center of a vastly larger structure without knowing it. Such models require abandoning the cosmological principle. They place us in a special location, not necessarily at the exact center, but somewhere within a spherically symmetric structure. Current observations don't require such models. They fit data no better than the standard centerless model. But they remain possible. The choice between centerless and centered models ultimately rests on philosophical grounds as much as observational ones. Scientists prefer the centerless model because it doesn't require Earth to occupy any special position. The Copernican principle, that we're not cosmically special, has proven reliable historically. Every time humans assumed centrality, we turned out to be wrong. But this preference isn't proof. Perhaps the universe really is structured with a center. Perhaps we happen to live relatively near that center. The odds seem astronomical. Why would random chance place us near the middle of such an enormous structure? Yet astronomical odds don't equal impossibility. Testing these alternatives requires observations beyond current capabilities. Looking for patterns in the cosmic microwave background that might indicate large-scale topology. Searching for repeating features that would suggest space wraps around on itself. Measuring expansion rates with unprecedented precision to detect any asymmetry. Future telescopes might provide answers. The James Webb Space Telescope peers deeper into cosmic history than ever before. Next-generation gravitational wave detectors could reveal large-scale structures invisible to electromagnetic observation. Better understanding of dark energy might constrain possible geometries, or we might never know. If the universe extends far beyond our observable horizon, the question of whether it has a center becomes fundamentally unanswerable. We're limited to our local cosmic neighborhood, unable to see or measure the broader structure. This limitation doesn't render the question meaningless. Understanding what we can and cannot know helps define the boundaries of science itself. Some questions may lack empirical answers, while remaining conceptually important. The universe might have properties we can never directly verify. Consider the implications of an infinite universe. If space extends without bound, then not only does it lack a center, but it contains infinite matter and energy, infinite galaxies, infinite stars, infinite planets. Somewhere in that infinity, every possible configuration of matter eventually occurs, including exact copies of Earth, of you, of this moment. The idea sounds absurd, yet mathematical infinity demands it. Given infinite space and finite possible arrangements of particles within any region, repetition becomes inevitable. Not just similar configurations, exact duplicates down to every quantum state. Infinitely many of them. This conclusion follows logically from infinity itself. If the universe is truly infinite and matter is distributed roughly uniformly on large scales, then identical regions must recur. The probability of any specific configuration might be astronomically small, but infinity contains all probabilities, no matter how unlikely. Finite universes avoid this strange conclusion. A universe that wraps around on itself like a torus has finite volume. It contains a large but countable number of particles. No duplicates need exist. Your consciousness remains unique, however vast the cosmos. The question, does the universe have a center, thus connects to profound issues of identity, uniqueness, and the nature of existence itself. The answer shapes how we understand our place in reality, whether we're one among many or truly singular, whether location carries meaning or represents arbitrary coordinates. These philosophical tangents might seem distant from observational cosmology, but science never operates in pure isolation from human concerns. The questions we ask reflect what we want to understand about ourselves and our relationship to the cosmos. Whether we're central or peripheral, special or ordinary, unique or repeated. The centerless universe delivers a clear verdict on some of these questions. Not central, not special in location, but the answer to uniqueness depends on whether infinity applies, and that remains unknown. Living with uncertainty about such fundamental questions requires intellectual humility. Science provides powerful tools for understanding reality, but those tools have limits. Beyond the observable horizon lies territory we can theorize about but never directly explore. This doesn't mean abandoning the quest for understanding. Each generation of astronomers pushes the boundaries further. Telescopes see deeper. Measurements grow more precise. Theoretical frameworks become more sophisticated. The edge of knowledge advances even if ultimate answers remain elusive. What we know today vastly exceeds what earlier generations could have imagined. Ancient astronomers couldn't conceive of galaxies beyond our own. Medieval scholars lacked the mathematics to describe curved spacetime. Even Einstein initially resisted the idea of cosmic expansion. Each conceptual revolution required abandoning cherished assumptions. Earth isn't the center. The Sun isn't the center. The Milky Way isn't the center. Now we learn the question itself may be misguided. Centers don't apply to the cosmos as a whole. Future revolutions likely await. Perhaps our understanding of space and time will undergo another transformation, as radical as Einstein's. Perhaps quantum gravity will reveal structures beyond current imagination. Perhaps the multiverse concept will gain empirical support or face definitive refutation. The centerless universe represents our best current answer, not our final word. Science remains perpetually open to revision when new evidence demands it. The confidence we place in this conclusion reflects the strength of supporting evidence, not absolute certainty. That evidence is substantial. Multiple independent measurements all point the same direction. The cosmic microwave background's uniformity, galaxy distribution's large-scale homogeneity, supernovae indicating uniform expansion, gravitational lensing revealing matter distribution. Everything fits the centerless picture. Yet extraordinary claims require extraordinary evidence, and claiming the entire universe has no center qualifies as extraordinary. The evidence, while strong, comes from limited perspective. We see only our cosmic neighborhood, not the whole of existence. This limitation doesn't invalidate the conclusion. Working with incomplete information characterizes all science. We build models explaining observations while acknowledging uncertainty. The centerless universe explains what we see without requiring special assumptions about our location. Alternative models requiring Earth to occupy special positions face the burden of explaining why. Why would random chance place us near any cosmic center? Why should our location be anything other than typical? The cosmological principle offers elegant simplicity. Everywhere is equivalent because no location is special. So where does this leave the original question? Does the universe have a center? Based on everything we can observe, no. Based on our best theoretical understanding, no. Based on the philosophical principle that we don't occupy privileged positions, no. But with the caveat that certainty eludes us. The universe might have properties beyond our observational reach, structures on scales we can't detect, geometries we haven't imagined. The cosmos has surprised us before and likely will again. What we can say with confidence: if a center exists, we've found no evidence for it. Every test designed to detect centrality has failed. Every measurement suggesting special locations has been explained by other means. The universe appears profoundly democratic in its structure. This democracy extends from the largest cosmic scales down to human experience. Your observation point matters just as much as any other. The view from Earth carries the same weight as the view from any distant galaxy. No cosmic hierarchy privileges certain perspectives over others. In a universe without center, every location becomes the center of its own observable sphere. You stand at the middle of everything you can see, not because you're special, but because observation defines its own reference frame. This democratic cosmos removes cosmic hierarchy without removing cosmic significance. The question of the universe's center thus resolves into something subtler than yes or no. It transforms into an exploration of what centers mean, how observation shapes perspective, and why the cosmos appears structured as it does. The answer reveals as much about human cognition as cosmic architecture. We're built to find centers, to establish reference points, to orient ourselves in space. These mental tools served our ancestors well navigating earthly landscapes, but they mislead when applied to the cosmos itself. The universe operates according to principles that transcend human intuition. Understanding this requires reconceptualizing space, time, and existence, not as absolute containers with fixed properties, but as dynamic, relative, observer-dependent aspects of reality. The center you seek doesn't exist because the question assumes a framework that doesn't apply. This might feel unsatisfying. The human mind craves definitive answers, clear boundaries, absolute truths. But reality doesn't always accommodate these preferences. Sometimes the deepest understanding comes from recognizing what questions don't have answers, not because we lack knowledge, but because the questions themselves rest on faulty premises. Looking back across this entire journey, you might notice something curious. We started with a simple question: does the universe have a center? and ended up somewhere completely different. Not with an answer exactly, but with an understanding that the question itself misses the point. This happens sometimes in science. You chase one problem and discover the real insight lies in why the problem was unsolvable. The universe doesn't have a center, not because we haven't found it, but because centrality is a concept that emerged from human experience with bounded objects. And the universe isn't an object. It's the framework within which objects exist. Every piece of evidence points the same direction. The cosmic microwave background arrives uniformly from all directions. Galaxies distribute themselves homogeneously on large scales. Expansion proceeds at the same rate everywhere. No rotation, no curvature center, no privileged location. The observations don't just suggest there's no center, they make centrality meaningless as a cosmic property. But here's what strikes me as genuinely profound about this conclusion. It's not depressing, it's liberating. You occupy a position in the cosmos that has exactly the same status as every other position. Not worse, not better, equivalent. The view from Earth matters as much as the view from anywhere else. Your observations carry the same weight as observations from any distant galaxy. The universe's structure doesn't privilege anyone's perspective. This cosmic democracy means something important for how we think about existence itself. We spent centuries fighting to escape the assumption that Earth was cosmically special. That battle is over. We're not special by location, but neither is anyone else. Everyone gets equal standing in the cosmic order. The observable universe appears to be our permanent prison in a sense. Light from beyond the cosmic horizon will never reach us. Regions too distant for causal contact remain forever beyond knowledge. We can theorize about them, build models describing them, but we'll never observe them directly. Our cosmic bubble defines the limits of possible knowledge. Yet within that bubble, we've learned something extraordinary. The universe at its largest scales operates by rules that violate every intuition built from everyday experience. Space expands without expanding into anything. Time began without a before. The Big Bang happened everywhere simultaneously, and the entire cosmos lacks any central reference point. These aren't failures of understanding, they're successes. Each violation of intuition represents a deeper truth about reality. The universe doesn't conform to human expectations because it wasn't built for human convenience. It operates according to mathematical principles that transcend our cognitive limitations. General relativity describes spacetime as a dynamic entity that curves in response to matter and energy. Apply those equations to the universe as a whole, and centerless expansion emerges naturally. Not as a surprising result requiring explanation, but as an inevitable consequence of the underlying mathematics. The theory practically demands it. Observations confirm what theory predicts. This convergence between mathematical structure and empirical measurement gives us confidence the centerless model captures something real. Not just a convenient fiction or mathematical abstraction, but an accurate description of cosmic architecture. Still, uncertainty remains. The universe beyond our horizon remains unknown. Alternative models exist where large-scale structure violates homogeneity. We can't definitively rule out every possibility. Science works with probabilities and evidence, not absolute certainty. The cosmological principle, that the universe looks the same from all vantage points on large scales, remains an assumption. a well-tested assumption supported by overwhelming evidence, but an assumption nonetheless. We extrapolate from our local observations to make claims about the entire cosmos. That extrapolation might fail beyond scales we can measure, but the principle has proven remarkably robust. Every test designed to detect violations has failed. Every measurement suggesting inhomogeneity has been explained by smaller scale structure. The pattern holds across every scale we can observe. This doesn't prove the pattern continues forever. Perhaps at some enormous scale beyond our detection, the universe becomes lumpy, asymmetric, centered. We can't rule it out, but we have no reason to expect it either. The simplest extension of what we observe suggests homogeneity all the way down, or all the way out rather. Living with this uncertainty represents part of the human condition. We want definitive answers to ultimate questions. Does the universe have a center? Is it infinite? Will it last forever? These feel like questions that should have clear yes or no answers. Reality doesn't always cooperate. Some questions remain perpetually open, not because we lack sufficient data, but because the questions probe beyond what observation can ever reach. The universe's total extent, its ultimate fate, its structure beyond our horizon, these might remain forever unknown. That doesn't make them meaningless. Understanding the boundaries of knowledge helps define what science can and cannot accomplish. Some mysteries resist solution not from inadequate tools, but from fundamental limitations on what's knowable. The question of cosmic center has a clearer answer than most. Everything we can measure says no. Everything we can calculate says no. Everything we understand about physics says the concept doesn't apply. That's as close to certainty as cosmology gets. You're floating through space on a planet, orbiting an ordinary star in an unremarkable galaxy. That galaxy participates in the expansion of space, along with hundreds of billions of others. No location is special. No direction is privileged. No reference frame is absolute. This might sound lonely. Cast adrift in a centerless void with no absolute coordinates, no cosmic landmarks, no way to define where you truly are. But flip the perspective one more time. Every point in this centerless universe serves equally well as the origin of a coordinate system. You can define yourself as the center of your observable sphere. Not because you're cosmically special, but because observation creates its own reference frame. The universe arranges itself around you in concentric shells of increasing distance and look-back time. An observer in the most distant galaxy we can see would experience the exact same thing. They'd be at the center of their observable universe, seeing galaxies distributed around them in all directions. Their cosmic horizon would be different from ours, overlapping but not identical. Billions of observers throughout the cosmos each occupy the center of their own observational bubble, all equally valid, all equally central in that limited sense, which is another way of saying none of them are central at all. The universe has no center because every location has equal claim to centrality. That's not a failure of the cosmos to provide what we expected. It's a feature revealing something profound about the democratic structure of reality itself. Physical laws apply uniformly everywhere. No location gets special treatment. No position enjoys privileged status. The same quantum mechanics, the same gravity, the same electromagnetism operates throughout the observable universe, probably throughout the entire universe, observed or not. This uniformity, enables cosmology as a science. If different regions followed different laws, we couldn't extrapolate from local observations to cosmic conclusions. The centerless, homogeneous universe makes understanding possible. Its very democracy allows knowledge. We've traced cosmic history from the Big Bang forward through 13.8 billion years of expansion and structure formation. We've mapped the distribution of galaxies across billions of light years. We've measured the afterglow of creation itself in the cosmic microwave background. And through all of this, one truth emerges consistently. No center, no edge, no privileged position. Just space expanding uniformly, carrying matter along with it, creating new distance between distant objects, while local structures remain bound by gravity. The Big Bang happened everywhere at once, because everywhere was the same place, compressed to unimaginable density, then expanding into the universe we observe today. Your current location participated in that event just as fully as any location billions of light years away. You exist at a point that was present at the beginning of time. So does every other point in the cosmos. There's no ground zero to visit, no cosmic origin point to make pilgrimage toward. The origin is everywhere and nowhere. The beginning happened at a time, not a place. This represents perhaps the final step in humanity's long journey away from cosmic centrality. Not just that we're not at the center, but that center itself is a concept that doesn't map onto cosmic structure. The question dissolves under examination. What remains is something stranger and more beautiful. A universe where every location matters equally, where every observer gets their own unique but equivalent perspective, where the view from Earth carries the same cosmic weight as the view from anywhere else. The cosmos offers no hierarchy of position, only the profound democracy of a centerless, expanding space where existence itself is evenly distributed across scales too vast for human comprehension. You're not at the center of the universe, but you're not on the edge either. You're exactly where the mathematics of cosmic expansion puts you, somewhere in the middle of your own observable sphere, watching distant galaxies recede in all directions, participating in the same universal expansion that governs every other location. That's the answer. Not a point on a cosmic map, but an understanding that the map itself has no center point. The universe is structured such that the question, where is the center, has no meaningful answer. Not because we don't know, but because the question assumes something that doesn't exist. The human journey from geocentrism to this final understanding took centuries. Each step required abandoning cherished assumptions about our cosmic importance. Earth isn't the center. The sun isn't the center. The Milky Way isn't the center. And now, most humbling of all, there is no center. But this final humbling comes with unexpected grace. In a centerless universe, every position holds equal status, yours included. The cosmos doesn't privilege any perspective, which means it privileges all perspectives equally. You matter not despite being nowhere special, but because being nowhere special is exactly what every location in the universe shares. That's where the question leads. Not to a point in space, but to an understanding of space itself. Not to coordinates marking a cosmic origin, but to the recognition that origins don't work the way our intuition suggests. Not to an answer that satisfies our craving for centrality, but to a deeper truth about the democratic structure of reality. The universe has no center because it doesn't need one. Every point participated equally in cosmic history. Every location expands at the same rate. Every observer sees the same large-scale patterns. The center is everywhere, which means it's nowhere at all.